Hi, everyone. So I wrote this blog post on mixture of experts and expert choice. These are known as routing algorithms for LLMs or for neural networks. And the mixture of experts was pioneered in a 2017 paper by Noam Shazeer. I'm going to walk through my own methodology on how I derive mixture of experts and how I end up at the same exact formulation that Shazeer does. So I'm going to talk about some motivation behind the problem, a brief bit of the history, and then we'll incrementally work our way to that final formulation. So to understand mixture of experts and why it looks the way it does, it helps to take a step back and just understand expert functions in a general sense. And the reason why that's useful is because oftentimes when you're implementing an algorithm, you want to look at what already exists and try to minimally adapt that so that it works for a use case. So expert networks has a slightly different motivation, which is that you have n networks, we'll call them f sub I, and these expert networks are specialized for different tasks. And when we receive some input, x, we want to figure out some combination of the outputs of the expert networks that should most accurately predict the output for f of x. So that's what we're constructing here. And the way that it works intuitively is that each of these networks gets some weight. Maybe one of the experts that we're really confident in gets 0.75, and another expert that we're not so confident in gets 0.05. And we're just going to take a linear combination of the expert network's outputs. We're going to add it together, and that's the final output. And if you've constructed probability distributions that are learned in neural networks, then you'll know that a very common way of doing this is you construct some logits, meaning you construct just plain real numbers that are raw, not normalized for each of the elements of the probability distribution, and then you normalize those elements. So that's exactly what's described here. The notation is a little bit funny, but it takes x, which is the input to the expert networks. It computes some linear transformation, and this is referring to the ith element. So z is some vector that contains logits, one for each expert network. These elements of z are normalized using a softmax distribution, and you end up with a vector called g, where each of the elements of g corresponds to the weight that that expert network gets. And then this is just a linear combination. We just sum up each of the f sub I weighted by g sub I. So the problem with this is that you still have to compute every single f sub I. Even if an f sub I has a very low weight, we really don't think it's going to be useful for this token. We still have to compute it. So that motivates the idea of gating. We're going to start with top one gating, which is the idea that we only select the top expert network, and that's the output that we produce for the aggregate function. Of course, you could have some generalized concept for this, like top k gating, where we look at the top k expert networks. And by default, the original expert network formulation is essentially top n gating. Every single expert network is used. So for top one gating, we define it formally. We would compute all the g sub I, so all of those probabilities. We select the top g sub I, we'll call that s, or g sub s to refer to the probability, and then we just compute the output, g sub s times f sub s. What's weird about this is that we're still weighting f sub s. Even though it's top one gating, you might think, let's just take the top expert and output whatever that expert produced. You still end up weighting it by g. And there are some ad hoc justifications for why you would still want to weight or scale the output of f. In practice, the reason why we scale it is because it just works better in training and in simulation. So that's the version of top one gating that everyone uses. All right, so first I want to talk about these backpropagation rules. So there are two sets of parameters that we want to update. And for those who are familiar with gradient descent, the way that you update a set of parameters is you need to compute the loss with respect to the set of parameters that you want to update. So that's what I'm writing down here. We have a couple of functions. We have g and f. G is a single vector with probabilities for each entry, and f is a set of vectors. Each f sub I is its own vector. So this is how we compute those gradients. Let's assume that you have some loss function, which is a function of the output y, so L of y. We want to compute L with respect to theta, the change in theta sub f sub s. So I just break this expression up. It's change in L with respect to y. G sub s is constant if you're differentiating theta sub f sub s. and then you need to differentiate f sub s. So that's the expression that's written here. For the experts I that are not equal to s, their output does not change even when we update this theta. And therefore their gradient is not going to, or their output will not impact the loss. They weren't factored into the loss because we only picked the top one expert. So all of those gradients are equal to 0. Then there's the second gradient, which is change in loss with respect to theta sub g sub s. And s is the expert that we selected. Again, you can differentiate the expression above. Now the catch with g is that the experts that are not selected are also going to change. Those gradients are not going to be equal to 0 with respect, if you're computing the change in the loss function with respect to theta sub g sub I. And the reason for that is that g is normalized. So if you upweight or downweight some expert network that's not equal to g sub s, or that's not equal to s, then that will impact the output of g sub s. So I just make that note here. And then I note the major failure case, which is that if a network is not selected, then we're basically not going to update it. And it's that point that I made earlier, which is that if I is not equal to s, or if I is not the expert network that we selected, then the change in the loss function with respect to that expert network's parameters is going to be equal to 0. And that's an issue because let's say you start off with some random distribution where one network receives 80% of the tokens, that means that that expert's going to improve the most. That means that its loss is going to go down the most, and G is going to continually throw more and more tokens at it. So you'll end up with a collapse of your training process. So what that implies is that we want some distribution of G that's kind of uniform-ish. I'm not saying that it's uniform for any individual G of X. Of course, for a given G of X, you'd hope that G learns that expert I is better than expert J. But across the whole distribution, so across a whole batch or across the whole data set, in general, you want G to evenly route tokens to each of the expert networks. So I'm just writing out one possible regularization that you might write if you were trying to define this naively. So you define the proportion of tokens that are actually routed to expert I. This is just some indicator variable that indicates whether at that time step we selected expert I. And then we compute the average or the expected number of tokens or the average number of tokens that was routed to expert I. And then you would regularize this. Maybe some KL divergence where you try to keep P close to a uniform distribution or some other form of regularization. The problem is that this doesn't work. And the issue is that P sub I depends on an argmax implicitly. This indicator variable is selecting the S sub T such that G sub I is the greatest. And at almost all points, the gradient of P sub I is going to be 0 then. Because unless you're exactly at the boundary where one expert would be selected over another, then in general, the output's not going to change. So we have to take a different approach. And the approach that Shazeer takes is he creates a soft differentiable sampling process. I'm just going to note that this is not the distribution that Shazeer uses. This is just the distribution that I decided on, and I end up at the same result as him. But of course, you can take different routes and end up at the same function for mixture of experts. So the constructive process that I naturally came to involves Gumbel noise. So the reason why I picked Gumbel noise as the noise distribution on the logits is because you can use the Gumbel max trick. The Gumbel max trick is a way that you can cleanly compute what's the expected proportion of tokens that will be routed to a given expert I. So I'm just writing out exactly what the statistical process looks like formally. So those logits that we computed earlier, let's assume that we're actually observing a noisy version of them. So that has this noise, epsilon sub j, for a given expert j. And the Gumbel max trick tells us that the maximum value across these logits, so let's say you took each logit, z sub I, you add some Gumbel noise to it. You do that for all of the logits. If you select the maximum element after the noise is added, then it's going to follow this really clean categorical distribution. And you might remember that softmax z is how we defined G. So in other words, G exactly specifies the probability that an element after the noise addition will be selected as the maximum. So that's just what I talked through in this section. And once you have the probability, then you can, of course, compute the expected load across a given batch. You just add up those probabilities for each of the tokens. That gives you the expected load. And then you can minimize that using some sort of regularization like we were discussing before. So these are some different regularizations that I proposed. The one that Shazeer uses is this one called coefficient of variation. And they actually square it so that it's nicer for the optimization. But this is what the full loss looks like after you've added that auxiliary loss. And for those of you who are familiar with mixture of experts, you might note that this is not the version of mixture of experts that's used today. In fact, people use this other auxiliary loss instead, and it doesn't look very much like the one from before. What I'm going to walk through here is how you might end up at this surrogate auxiliary loss, even though you were starting at the same fundamental assumptions that we were working with before. And in practice, the reason why people use this is because it's just faster to compute, and it still works reasonably well. But I'm just giving some theoretical justification for it. So we wanted the proportion of tokens routed to each expert to be roughly uniform. So this is one way that you could write an optimization function that has the uniform distribution as a result. So if you wanted to minimize the square of each of the proportions, and you constrain that optimization such that the proportions all have to sum to 1, then minimizing this objective is the same thing as a uniform distribution. And you can derive this through the method of Lagrange multipliers. So let's say that that is the objective that we want. Then we can create a surrogate of this objective where you can estimate P sub I using G sub I. Using the same methodology that we were talking about before, you can take the probability that a token is routed to expert I and sum that probability across each of the elements in the batch. The average value of those probabilities should be, in theory, equal to P sub I. So we substitute that into the optimization, and you end up with the exact same surrogate that people use in practice. So that's not really the reason why people ended up at this surrogate. I think that they just tried it out and maybe intuitively they understood that this was kind of what it was doing. But this is one way that you could theoretically derive it. And I just want to note that I feel like the Gumbel and noise version, where you actually are injecting Gumbel noise and then you're computing the exact probability that one of those maximum values is selected, is actually a cleaner formulation. And if only the world worked so that the cleanest mathematical formulation was also the one that worked the best in practice. In practice, this surrogate is the one that works better in practice. So this is the one that people use. Usually for mixture of experts, you don't want to just pick one expert though. You want to pick the top K. And that's because maybe one expert is a little bit noisy or it has some variance. So you can even that out by picking K experts. And you can define it pretty similarly to how we did above. Instead of P sub I being the probability that I is the top expert, now we're going to say Q sub I, which is some other version of basically P sub I, is the probability that I belongs to S, which is the subset of the top K experts. And unfortunately, there's not a really clean Gumbel max trick like we had before to compute this probability. What we do have is a distribution called the Plackett-Luce distribution, which does follow this distribution of top K sampling. But the problem is that it's not very easy to compute. So that gradient, if you directly computed it, would be computationally intractable. So as a result, people end up using the same surrogate that we defined above, even for top K experts. So I just want to note one last time that this is not the set of steps that Shazeer goes through. He adds normal noise to the logits instead, and he renormalizes the weights G sub I after selecting the top K elements. So the statistical process that he's using is different than the one that I'm assuming here. It just so happens that the result is the same. I thought that this derivation that I went through was helpful for myself, and I hope that it was helpful for you too. I'm not going to talk about expert choice in this video, but I appreciate any comments and let me know if you'd like me to walk through any other methods.